Let's talk about something that's literally all around you, shaping everything from the phone in your hand to the car you drive, but you probably almost never think about it. It's the invisible architect of our world, mechanical design. And today, we're going to pull back the curtain.
So let's start with a little thought experiment. Picture a race car, all power, noise, and raw force. Now picture a surgical robot, something that has to be incredibly precise, gentle, and delicate. I mean, they feel like total opposites, don't they?
Well, believe it or not, they're both speaking the exact same language. A fundamental language of forces, materials, and function. That's what mechanical design is. It's the universal rulebook for how we turn an idea into something that actually works in the real world. So let's dive into the 3 core principles of this invisible architect.
Okay, first things first. It doesn't matter how brilliant a design is if it breaks the first time you use it. So the number one job for any engineer is to create something that can actually survive the real world. All the stress, the wear, the tear, it's all about durability.
And one of the biggest enemies in this fight is something called metal fatigue. You know how you can bend a paperclip back and forth? It's fine the first few times, but if you keep doing it, that repeated stress just weakens the metal until snap. That's fatigue. And it's basically the silent killer that engineers are constantly designing against.
And as you can see here, this isn't some minor issue. We're talking about things where failure is simply not an option. The crankshaft spinning in your engine, the steel rails holding up a massive train, or the turbine blades in a jet engine. In these situations, predicting and preventing that snap isn't just good engineering, it's a matter of life and death.
And that's the key. The game has totally changed. It's not just about brute forcing a design by making it super thick and heavy anymore. Today, it's a proactive science. It's about using incredibly powerful simulations to predict and manage the risk of failure before a single piece of metal is even cut.
So once you've figured out how to make something survive, the next big question is, how do you make it thrive? How do you make it the best it can possibly be? And that brings us to our second principle, optimization. This is the constant push to make things lighter, stronger, faster, and way more efficient.
Now, what's so cool about this is how it completely flips the old way of thinking on its head. Traditionally, design was like sculpting. You'd start with a big block of metal and just carve away everything you didn't need. This new approach does the exact opposite. It starts with nothing, and an algorithm adds material only where it's absolutely needed for strength. It's not just more efficient, it's smarter.
And this new method is called generative design. It's pretty wild. An engineer basically just gives the computer a set of rules like, I need a part that can hold this much weight, costs less than this, and is made of aluminum. Then the AI goes to work, generating thousands of possible solutions. A lot of them look kind of weird and alien, like something out of nature. The engineer's job then becomes less about drawing and more about being a curator, choosing the absolute best option from this huge menu of possibilities.
And the results? They're just staggering. Take a look at this part for a drone. Using optimization, they managed to slash the weight by 60% while making the part 20% stronger. I mean, come on, that's a leap in performance you just couldn't get with the old way of doing things.
All right, so our design is tough. It's super efficient, but it's still useless if a person can't actually use it, right? This brings us to our third and maybe the most important principle, designing for us, for people. This is all about ergonomics, safety, and more, looking for clues from the greatest designer of all, nature.
And the range of applications here is just incredible. We're talking about soft robots inspired by nature for delicate surgery, exoskeletons that give people their strength back, and even safety systems for kids' toys. There are even vision systems for machines inspired by the legs of kangaroos and fleas. Turns out, nature has already solved a lot of our toughest problems.
This table just nails the contrast. On one side, you have that surgical robot. Its whole goal is gentleness, so it uses soft materials to help a surgeon. On the other, you have a giant industrial robot. Its goal is pure power and speed, so it's made of rigid steel, and the main human factor is just keeping the operator safe from all that force. It's the same principles, just tailored for completely different human needs.
So we've got survival, we've got optimization, and we've got designing for people. But what's next? Where is all this headed? Well, the future is all about the tools themselves, and they are starting a revolution in what we thought was even possible.
I mean, just look at this timeline. In the span of a single human life, we've gone from people doing calculations by hand at drafting tables to computers that can digitally build and stress test a part before it even exists, all the way to the AI-powered partners we have right now. The pace of change is just accelerating like crazy.
And one of the most powerful ideas emerging from this is the digital twin. Okay, this sounds like sci-fi, but it's real. Imagine creating a perfect, living, virtual copy of a real-world object, like a huge wind turbine. This digital twin is hooked up to the real one, getting live data on everything: wind speed, stress on the blades, power output. It lets engineers test out new ideas, predict when a part might fail, and optimize its performance in real time, all without ever leaving their desk.
And this is the number that really changes the game. In less than a single second, an AI can dream up and test thousands of different design ideas, a task that would take a whole team of brilliant engineers months, if not years. We're not just talking about being faster. We're talking about unlocking a level of creativity that was physically impossible for us before.
So I want to leave you with this question. As our tools stop being just tools and start becoming intelligent, creative partners, the whole game is changing. The next time you look at any piece of technology, think about that invisible architect. And ask yourself, with tools like these, what are the truly profound problems we'll finally be able to solve?